Alright, hello everybody. So today we're talking about Taylor and Maclaurin series. So suppose f is a function represented by a power series and remember, a power series is going to say something like f of x equals the sum from n equals 0 to infinity of Cn, so that's a function of n, so that's the coefficient as a function of n, times x minus a to the power of n. And if you were to write this out, then this would be, you get C0 plus C1 times x minus a plus C2 times x minus a squared plus, and so on, right? Because the next term would be C3 times x minus a cubed, then C4 times x minus a to the fourth, and so on. And let's say we wanted to take f prime of x. So let's say we wanted to take the derivative of this thing. Then what we learned earlier is that we can just take the derivative of each term. So if we take the derivative of each term, we're going to get C1 plus, if you now, so take the derivative of a constant, that goes away. Take the derivative of this term, you just get C1. Take the derivative of this term, again, you're having to use the chain rule, but the derivative of the inside function is just 1. So if you take the derivative of this, you would pull out the 2, so you get 2 times C2 times this inside function, x minus a to the power of 1. Right? And then you just keep going. So plus the next term, you would pull out the 3, so you get 3 times C3 times x minus a squared, and so on. So 4 times C4 times x minus a cubed, or wait, sorry, yeah, and so on, right? It just keeps going, right? And let's see what happens. So, and let's see what happens when you take the second derivative. Then what you're going to get is going to be, well, this constant term is going to go away. If you take the derivative of this one, you're going to get 2 times C2, plus if you take the derivative of this term, you're going to get 2 times 3 times C3 times x minus a, plus if you take the derivative of this term, you're going to get 4 times 3 times C4 times x minus a squared, and you just keep going, and so on. Right, so this is just analyzing what happens whenever we take our derivatives, and I'll say so on and so forth. Right, so you can just keep doing this, keep taking derivatives, but let's say here, what happens if x is equal to a, right? Because that looks like a special case. So if x equals a, then what's going to happen here is we've got f of a, right? So we just plug in a to what we had up here. Well, notice if we plug in a, this goes away, and everything to the right also goes away because all of them have a factor of x minus a. So the only thing you're left with is C0. So I'll just write out what I said there. So it's C0 plus C1 times 0 plus C2 times 0, and so on. So what you're going to get is C0. So f of a equals C0. And let's see what happens whenever we have f prime of a. Right, so we'd look at the derivative, and if we plug in a, then all of this stuff is going to go away, and we're just left with C1. So we're going to have C1 plus 2C2 times 0 plus 3C3 times 0, and so on. And eventually we just get C1. So f prime of a equals C1. And let's look at what happens, just this one last thing. Let's say we have f double prime of a. Then again, we just plug in a here, everything to the right goes away, and we're going to get 2c2 plus 2 times 3 times c3 times x minus a, and so on. This is 0 since we're plugging in a. And everything to the right is also going to be 0 here. So again, we're going to get 2 times c2. So f double prime of a equals 2c2. And let's just do this one more time just to figure out what the pattern is. So f triple prime of a, if we do that, if we take the derivative one more time, then this is going to be the only term that we have that's non-zero. So we're going to get 2 times 3 times c3 plus 2 times 3 times 4 times c4 times x minus a. This is supposed to be an x. And so on, because everything to the right is going to have more copies of x minus a. But if you plug in a, you get f triple prime of a. Then all the stuff to the right again goes away, so you get 2 times 3 times c3. Which, notice, is the same thing as 3 factorial times c3. Okay, so let's just write down what we had. We had f of a equals 0 factorial times c0, because remember, 0 factorial is the same thing as 1, right? It's just 1. And if we had f prime of a, then we're going to have 1 factorial times c1, which is just c1, so that's what we got there. If we have f double prime of a, we get 2 factorial times c2, which again, 2 factorial is just 2 times 1, so that's just 2. F triple prime of a was going to be 3 times 2 times 1, so it's 3 factorial times c3, and so on, right? This is just going to keep going. So what we can say here is that in general, we're going to have that the nth derivative of our function f at a is going to be equal to n factorial times cn. That's our pattern that we have. Or if we solve this equation for cn, then we're going to have that cn equals the nth derivative of f at a over n factorial. And here, I'll say here, we assume that 0 factorial equals 1, and if you take the 0th derivative, we're just going to say that that's the same as our original function, f, right? So c0 is going to be the original function f evaluated at a over 0 factorial, and 0 factorial is 1. Okay, so we've actually figured out, just by doing this analysis, how to convert this, how to figure out exactly what the constants are in this function, right? So these functions of n that, or sorry, I shouldn't call them constants, coefficients is what I meant to say. These coefficients, we figured out exactly what they are. It's just the nth derivative at a over n factorial. So we have this very nice theorem. The point of all of this was to have a theorem. It's a very nice theorem, and it says if f has a power series representation at a, aka if f of x equals sum from n equals 0 to infinity of cn times x minus a to the power of n with the absolute value of x minus a is strictly less than r, then the coefficients Cn are given by Cn equals the nth derivative of f at a over n factorial. Okay, so notice this theorem looks very nice, but you have to be very careful with this theorem because it says in the beginning, if f has a power series representation at a, then you can go ahead and figure out what the coefficients are, and that's going to give you exactly what it is. But if f does not have a power series representation at a, then this is actually not going to make any sense, right? So this doesn't always work, but if there is a power series representation, this gives you exactly what the coefficients should be. So we can have a definition here. Let me write this down. Definition: a series of the form f of x equals the sum from n equals 0 to infinity of the nth derivative of f at a over n factorial times x minus a to the power of n. And if we were to write out the terms, this would be, so we would have f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus the next term would be the third derivative of f at a over 3 factorial times x minus a cubed, and so on, right? So that's just writing out all of the terms, just plugging in each value of n into here. This is what we get. If we have a series that looks like this, then a series of this form is called the Taylor series of f at a. Right. So this up here, this was our power series, and we said we can always, if we have a power series representation at this specific value of x, a, then if we have that power series representation, we can expand these coefficients using this formula, and if we do that, then we'd call this form of the power series the Taylor series. Okay. And you see one more thing in the title there. We also say Maclaurin series in the title. So let's say what a Maclaurin series is. So we just define the Taylor series. Let's see what the Maclaurin series is. It's very closely related. Okay. Here we go. So we get a special instance of Taylor series when a equals 0. And if that's the case, let's say a is equal to 0, then f of x equals the sum from n equals 0 to infinity. Remember, this was our formula here, and we're just going to let a equal to 0. So a is equal to 0, then we're going to have the nth derivative of 0 over n factorial times x to the power of n, because a goes away because a is 0. So if we just expand this one, then we're going to have f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so on. Right, so this is how we would add these things. Right, so it's f of 0 plus f prime of 0 over 1 times x plus, and so on. We just use the formula. So, sorry, what I meant to say, we get a special instance of this, and we call this the Maclaurin series. Right, so if a problem asks you find the Maclaurin series, then this is exactly the formula you use to find the Maclaurin series. You use the Taylor series formula, but you set a equal to 0. Maclaurin series of f. That's what I meant to say there. Okay, so let's go over an example. Example number 1 is going to say find the Maclaurin series of f of x equals 1 over 1 minus x. Okay, so something to check here is that we know, right, so previously we said that 1 over 1 minus x is actually going to be equal to the sum from n equals 0 to infinity of x to the n, right? So since we wrote this, then we can say that this must be the Maclaurin series too, right? Because if we have a power series representation, the theorem says if we have a power series representation, then we're able to rewrite it using the Taylor series. And notice here, what we have here, this is x to the n. Here we have x minus a to the n. So you can see here that a is equal to 0, which means that it is actually a Maclaurin series. So we actually already know that this is the Maclaurin series, but we want to check that fact. So how do we check it? We just manually compute exactly what this is. So that's our goal. So to check, so let's say here we have f of x equals 1 over 1 minus x. And if we plug in 0, then we're going to get f of 0 equals 1, right? If we plug in 0 there, we get 1. Let's say next we have f prime of x, right? So what I'm doing here is we need to take all these derivatives and evaluate them at 0. So I'm just going to take a bunch of derivatives of our function. So now we take our first derivative of the function. Remember, the way we do this using the chain rule is we rewrite this as 1 minus x to the power of negative 1, and then we take the derivative using the chain rule. Our answer is going to be 1 over 1 minus x to the power of 2. And if you plug in f prime of 0, you're again going to get 1. Okay, so we just keep doing this. F double prime of x is going to be equal to, we're going to get 2 times 1 over 1 minus x cubed. And if you plug in 0, then f double prime is 0. If you plug in 0 here, you're going to get 2. I'll say here it's 2 times 1. And let's just write out one more term here. Or sorry, one more derivative here. So let's just write out the third derivative. So f triple prime is supposed to be 3 primes of x is going to be equal to, so we take the derivative of this function. What we're going to get is going to be 3 times 2 times 1 over x minus, or sorry, 1 minus x to the power of 4. And let's say that we try to plug in 0, so f triple prime of 0. Then remember this is 0, so we're going to get 3 times 2 times 1. And if we just keep doing this, then we're going to get that the nth derivative evaluated at x, you can now kind of guess what this is going to be given the pattern that we've been writing down. So remember this was the third derivative. We had 3 factorial on the top, and then this was 3 plus 1. So our formula here is going to be n factorial over 1 minus x to the n plus 1. And if we have the nth derivative evaluated at 0, again, you can kind of guess using the pattern here. Here we had 3 factorial for the third derivative, so it makes sense if here we have n factorial. So that was just going off of the pattern, but the other way to see it would be to actually plug in 0 here. If you plug in 0, you're going to get n factorial. Okay. So therefore, we can say that Cn equals, remember our formula was the nth derivative of f at 0 over n factorial. But remember we said that this numerator was actually n factorial, so we're getting n factorial over n factorial, which is 1, right? Because you're just dividing something by itself. Okay, so again, we know that we can write 1 over 1 minus x as, so now we try using our formula, so it's the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the power of n. But remember we just calculated what this coefficient was and it was 1, so it's actually the sum from n equals 0 to infinity of x to the power of n, which is kind of already what we knew to be true. So we just checked that fact. That was this problem. We just needed to check this statement right here, and the way we checked it was we just took all of our derivatives, and then we knew that we needed to use this formula. So we needed to find what the nth derivative at 0 was, and once we figured that out, we could use the formula to solve the problem. Okay, let's do another example here. So example number 2 is going to say find the Maclaurin series for sine of x. And remember, this is the formula, again, that we're using. So, again, we're just going to make a table of derivatives. So, we're going to make a table on one side. We're going to have the nth derivative at x. And on the other side, we're going to have the nth derivative at 0. So we're just going to plug in 0 for whatever we get on the left-hand side. So let's say here, first we have f of x equals sine x. Okay, and now if we plug in 0 here, then f of 0 is 0. Okay, now let's take the derivative, f prime of x. So the derivative of sine is cosine. And now we plug in 0, so f prime is 0. Remember, cosine of 0 is 1. Now we take the derivative again. F double prime of x is going to be negative sine x, and f double prime of 0. So we plug in 0 there, and we're going to get, yes. So sine of 0 would be 0, so we're going to get 0 there. Now f triple prime of x. So if you take the derivative again, you get negative cosine x. And on the right side here, you plug in 0, so f triple prime of 0 is going to be -1. And now, lastly, we take our fourth derivative of f at x. And if we take the derivative of this function, the derivative of cosine is negative sine. They got that minus sign. That cancels out, so you get sine x. And now the fourth derivative of f at 0 is going to be, so you plug in 0 there, and you're going to get, again, 0. So what we can see from this is actually the derivatives repeat, right? Because you get sine x, and then eventually you get back to sine x, and then eventually if you do another 4 derivatives, you're going to get back to sine x again, right? So it's going to keep repeating itself. So we're going to keep swapping between 0, 1, 0, -1, 0, and it goes back to 1, 0, -1, and it's just going to keep going like that. So let's go ahead and write down what we have. So let me say what I said there, which was that the nth derivative at 0 repeats in cycles of 4. So let's just write out what we have. So if we try to use this formula, then what we're going to have is going to be f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus the fourth derivative of f at 0 over 4 factorial times x to the fourth, and so on, right? This is going to keep going. And now we can just plug in what we know, right? So here we know f of 0, f of 0, that's 0. F prime of 0, we said that's 1. So this thing here is 1. F double prime of 0, we said that that was 0. F triple prime of 0, we said that was -1. And f to the fourth of 0, we said that was 0. So if we just go ahead and collapse everything, all the zeros go away, and we can just rewrite these things as 1 and -1. So if we do that, then we're going to get the terms x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Right, so you can see here we're just getting the odd numbers, and we're alternating signs between 1 and -1. So if we tried to write this as a sum, we're going to have the sum from n equals 0 to infinity. So we know it's alternating, so we know that we need to have -1 to some power. And we know that the first term is going to have to be positive, right? So what that tells us is this should be n. Because here, if you plug in n equals 0 here, the first term is going to be positive. Okay, and then we're going to have x to the 2. Ooh, this is, let me use a different color here because this is a bit close together. So the next part here would be x to the power of 2n plus 1 over 2n plus 1 factorial. So the way I got that 2n plus 1 is I said, well, if these are odd numbers, we're taking the odd numbers here, then we can always rewrite the odd numbers as something like 2n plus 1, because this is always going to be an odd number. So if n is 0, this is 1. If n is 1, this is 3. If n is 2, this is 5, and that corresponds to the powers we see here. So we get 1, 3, 5, 7, and so on. So this is actually exactly the formula that we needed. So this is our answer here. This is our sum. So that's our answer. Okay. And now example number 3. Let me write this down. Okay. So example number 3 says find the Maclaurin series and find its radius of convergence for f of x equals e to the power of x. And this is a little bit sloppy, but this is e to the power of x. So we're trying to find this Maclaurin series. So again, our formula that we need, so we want to write f of x equals f of x equals, what I meant to say, e to the x equals the sum from n equals 0 to infinity of the nth derivative of f at 0 over n factorial times x to the n. Right, so again, whenever we're trying to find a Maclaurin series, this is the formula we need. And remember, for this, we need to figure out the derivative, and we need to figure out the pattern. So I'll write down here to find Cn, which is the nth derivative of f at 0 over n factorial. Note that. So let's think about what happens whenever we try to take the nth derivative of e to the x. Well, what's the derivative of e to the x? It's just e to the x. So if we take the derivative n times, well, it doesn't matter how many times we take it, we're still going to have e to the x. Right, so this is still going to be e to the x for all n. So if you take the nth derivative and you evaluate it at 0, then you plug in 0 here, e to the 0, that's going to be 1 for all n. Okay. So therefore, our coefficient Cn is equal to 1 over n factorial, and f of x equals e to the x equals, so we were going to have the sum from n equals 0 to infinity. We just plug in what we know here. We know the numerator here was 1, so we're going to have 1 over n factorial times x to the n, which is the same thing as the sum from n equals 0 to infinity of x to the n over n factorial. That'd be our answer there. Okay, so we figured out the Maclaurin series. This would be the Maclaurin series because we just had to use that formula. Now the second part says find the radius of convergence for f of x equals e to the x. We're trying to figure out when this series is going to converge, meaning if you add up all the numbers in this series, is it going to be equal to just some number, or is it going to be something that's oscillating between two numbers, or is it going to be something that goes towards infinity, right? So we're just trying to figure out whether this is equal to some number. And let's see if that's true. So we're trying to figure out when it's equal to a number, so we need to find, to find the radius of convergence, we need to figure out the values of x for which this is convergent. So the way we do that is always going to be using the ratio test, because the ratio test actually gives us a radius of convergence. So remember, for the ratio test, the thing we're calculating is the limit as n goes to infinity by the absolute value of an plus 1 over an. That's the thing we're trying to calculate. So if we do that, we've got the limit as n goes to infinity. The absolute value of if you plug in n plus 1 here, you're going to get x to the n plus 1 over n factor, or sorry, that's not what we meant to write. N plus 1 factorial. And we're dividing by just, if you plug in n, so we're dividing by this. But if you divide by a fraction, it's the same thing as multiplying by the reciprocal. So we're going to multiply by n factorial over x to the n. Okay. So now this is what we've got. And notice we can actually cancel some things here. So again, this is multiplying all the numbers that are less than or all the integers that are less than or equal to n. This is multiplying all the integers that are less than or equal to n plus 1. Notice all of the integers that are less than or equal to n being multiplied here cancel with the ones up here. So actually what you're left with is going to be, so the n, all the numbers less than n here, cancel with all these numbers, and you're just left with 1 over n plus 1, right? Because this is multiplying n plus 1 times n minus 1 times n minus 2, and so on. This is n times n minus 1 times n minus 2, and so on. You cancel out almost all those terms. You're just left with 1 over n plus 1. And here this is x to the n plus 1 over x to the n. This is n plus 1 copies of x multiplied together. This is n copies of x multiplied together. You cancel out n copies, and you're left with x over 1. Okay. And now notice n is going towards infinity, so this thing is going towards 0. So since this thing is going towards 0, we'd say that this is going to be equal to 0. And that is certainly less than 1. Remember, this was convergent if our number L here is less than 1. So this is actually always less than 1, no matter what the value of x is. So what we said with that was that r equals infinity. It's kind of a poor infinity sign. So we say here that r is equal to infinity because it doesn't matter what the value of x is. This series is actually always going to converge. So we'd say here that the radius is infinity. Okay. So the next thing to write down. So we're done with that example. Next, I'll say, in example 1, we already know that 1 over 1 minus x has a power series representation at this point. We don't know if f of x equals e to the x can also be represented by a power series. Even though we found its Maclaurin series. Okay, and I'll say here, we learned in example 3 that if e to the x has a power series expansion at 0, then it must be equal to sum from n equals 0 to infinity of x to the n over n factorial. So that's what we found, but notice this was only when we set a equal to 0, and this was assuming we could represent it as a power series. So at 0, at a equals 0, if we have a power series expansion, then this is what it is, but that's not exactly a guarantee that the thing exists. So let's actually look at an example involving this. So example, we're going to say consider f of x equals, so we're going to have a piecewise function. The first piece is going to be e to the power of -1 over x squared if x is not equal to 0, because notice if x is equal to 0, this is undefined. And if x is equal to 0, let's set this equal to 0. And let's just draw a graph of what this looks like. I guess I'll do it over here. So if we were to draw a graph of what this looks like, so these are our coordinates, and our graph would look something like this. It's going to look something like this, where as you get closer and closer to 0, you start really quickly, or as you start approaching x equals 0, you start really quickly approaching y equals 0. So what I'll say here is the Maclaurin series only needs the nth derivative of our function f at 0. And here, f of 0, so if we plug in 0 into our original function, then we're going to get 0, because that's what we say if x is equal to 0, our output is 0. So also, if we take the nth derivative of our function at 0, it turns out we're also going to get 0. This isn't, I don't like the way I worded this, but essentially what we're going to get, let me just erase this first part. But essentially what we get here is that the nth derivative of this function at 0 is also going to be 0 for all n. And what we can say here is then the Maclaurin series of f is, so we just plug this into the Maclaurin series, and we're going to get the sum from n equals 0 to infinity. We'll use this formula. We're going to get 0 times x to the n, which is just going to be 0 plus 0 times x plus and so on, we're just going to get 0. But f of x is not equal to 0 when x is not equal to 0. So our function f of x is not equal to the Maclaurin series. Right. So that's the important thing to notice here. What we said earlier was if it has a power series representation, then it should be equal to its Taylor series expansion. And specifically when a is equal to 0, it should be equal to its Maclaurin series expansion. But if it doesn't have a power series representation, then this isn't necessarily true. And as we saw here, our function is not equal to its Maclaurin series. So I'll say, so let's just intuitively think why this should be true. Let me just write this down. Okay. So intuitively, as x gets closer to 0, 1 over x squared gets huge very quickly. So e to the minus 1 over x squared approaches to 0 very fast. So there's no way a polynomial can keep up. Right, so that's kind of why you would think it should be true. And the key here is exponential growth versus polynomial growth. Right, exponentials grow a lot faster than polynomials do. So that's kind of why you would think that, well, it wouldn't make sense if we're actually able to represent this as a power series. So a question here is, so how do we figure out if e to the x is actually equal to what we said its Maclaurin series was, which was the sum from n equals 0 to infinity of x to the n over n factorial. All right, so how do we figure out if that's actually true? Or in general, if f of x actually equals its Taylor series expansion, which is the nth derivative at a over n factorial times x minus a to the power of n. So when is it actually true that a function is equal to its Taylor series expansion? And our answer is going to be when f of x, which is equal to the limit as n goes to infinity of the sum from n equals 0 to, sorry, from I equals 0, is from I equals 0 to n of this is supposed to be n of the ith derivative at a over I factorial times x minus a to the power of I. So whenever this thing, and if we look at the inside, so we're taking the limit of these would be called partial sums, because you're just adding together the first n terms, and you're taking the limit as n goes to infinity. So what we call this part is we call this part so we call it t sub n of x, which is equal to the nth degree Taylor polynomial. So we call this thing on the inside the nth degree Taylor polynomial, and we call this thing the limit of the sequence of partial sums, or when. So if we take f of x minus the limit as n goes to infinity of Tn of x, which is going to be the limit as n goes to infinity of Rn of x, which would call this part the remainder of the Taylor series. It's when this thing is equal to 0. So this is all just a little bit complicated. So in order to figure out whenever a function is actually equal to its Taylor series expansion, we have to go through these steps and validate that this limit of this remainder of the Taylor series is actually 0. But the takeaway is, if you do all of this work, then you can actually validate whether a Taylor series is equal to its, or whether a function is equal to its Taylor series expansion. But we're not going to worry too much about that. So I wouldn't worry about this stuff right here. So the point here is you're not able to just say that a function is equal to its Taylor series. There's a little bit more work involved. But I'll say for this section, the thing that we actually care about is just figuring out the Taylor series and the Maclaurin series. So that's really the point of this section. So I'll say here, we don't really care about that. We just care about finding the Taylor and Maclaurin series. So that's what we'll do in the next example. Okay. So, in example 4, let me use a different one. Just write one. It's not going to work. Use a different color here. So, example number 4, we're going to say find the Taylor series for f of x equals e to the power of x at a equals 2. Okay, so the Maclaurin series was at a equals 0, but instead we're going to mix it up a little bit. We're going to find when a equals 2. So remember here that the nth derivative of our function, remember that our function is e to the x, so our nth derivative is still going to be e to the x. So if we found the nth derivative evaluated at 2, it's just going to be e squared for all n. Okay, so now we write our Taylor series, which we said was the nth derivative and we're taking it at a equals 2, so the nth derivative at 2 over n factorial times x minus 2 to the power of n. That was our Taylor series formula for when a is equal to 2. And now we just plug in what we know. So this is the sum from n equals 0 to infinity of e squared over n factorial times x minus 2 to the power of n. And it turns out that this is actually equal to our original function. It's a little bit sloppy, but this is equal to e to the x. And I'll say here that the radius of convergence is also infinity. So you can go through and check this again using the ratio test, but it turns out that that's also going to be your radius of convergence. So you see here that we actually got two different representations of e to the x as power series. So we got, this was one of our power series representations of e to the x. This was a different one, and they're both correct. It just depends where you want the center to be to make the calculation a little bit easier, right? So here the center was at a equals 0. This was our Maclaurin series. So if you're picking values of x that are close to 0, this is probably the more convenient one to use. But if you're picking values of x that are closer to 2, then this is probably the more convenient one to use. So it's just a different way of finding a Taylor series, or a different Taylor series, just for a different value of that. Okay. And now let's go over the last example. So let me erase some more of the board here. So, final example for this section, number 5, is going to say, find the first 4 non-zero terms of the Maclaurin series for x times e to the x. Okay, so remember our formula is the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the n. So again, the same thing we did earlier. The first thing that we need to figure out is the nth derivative at 0. But notice we only need the first 4 terms, so we only really need to go up to the 4th derivative. Right. Well, we need the first 4 non-zero terms, so let's just keep going. Let's just do 4 derivatives. And then that'll probably be more than enough. So, remember our original function was x e to the x. Now our derivative of x e to the x, remember we need to use the product rule, so we're going to take the derivative of the first part here, so the derivative of that would be 1 times e to the x plus now the derivative of e to the x, which is e to the x times x, so we get x e to the x using the product rule, which you can rewrite as e to the x, e to the power of x times x plus 1. Okay, now let's take our second derivative, f double prime of x. So we know the derivative of e to the x is e to the x, and the derivative of this x e to the x we already found was this thing here. So plus e to the x plus x e to the x, because the derivative of x e to the x was this right here. Okay. And now we can rewrite this actually as e to the x times x plus 2, right? Because this is 2 times e to the x. And now if we factor out e to the x, that's what we get. And we can just keep going. The third derivative is going to be e to the x times x plus 3. And the fourth derivative is going to be e to the x times x plus 4. Okay, so we've kind of figured out what our derivatives should be equal to. Now let's try plugging in 0, right? Because we need to figure out these derivatives when we plug in 0. So f of 0, if we plug in 0 here, we're going to get 0. If we plug in 0 into this, f prime is 0, so we're going to get e to the power of 1 times, sorry, that's not what I meant to say, e to the power of 0 times 1, so we're going to get e to the 0, which is 1. Here, if we plug in 0, we're going to get 1 times 2, so f prime of 0, double prime of 0 rather, is 2. Here, if we plug in 0, we're going to get 3. Here, if we plug in 0, we're going to get 4, right? So if we're looking for the non-zero terms, well, certainly if we plug in n equals 0, then we're going to get 0 for this term, so we get rid of that. But then we look at the next terms after that. So what we can write, so sum from n equals 0 to infinity of our Maclaurin series is going to be equal to, so if we plug in n equals 0, we get 0. But then if we plug in n equals 1, we said this is 1, so we're going to get just x. Plus if we plug in n equals 2, so just check all of these. If you plug in n equals 2, you're going to get 2 over 2 factorial times x squared. If you plug in n equals 3, you're getting 3 over 3 factorial times x cubed. If you plug in n equals 4, you have 4 over 4 factorial times x to the 4th, and so on. So the first 4 non-zero terms are, so they would be, here we've got x, second term was x squared, the third term was 1/2 of x cubed, and the fourth term was 1 over 6 times x to the 4th. And you just keep going. And in general, let's say here, so we've answered the question, but I'm just going to say one more part here. In general, the nth derivative evaluated at 0 is going to be n. That's kind of the pattern that we saw here. So x e to the x is going to be equal to the sum from n equals 0 to infinity of n over n factorial times x to the n, which is going to be the sum from n equals 0 to infinity of, this would be, oh shoot, sorry, that's not what I meant to write. So notice what's happening here. If you plug in n equals 0, you're going to get 0. So you might as well start this at n equals 1 of n over n factorial times x to the n. So the reason these two are equal is because if you plug in n equals 0, you're getting 0 here anyways. So you might as well start at n equals 1. And then what you can do is you can cancel out, this is n times n minus 1 times n minus 2 and so on. You can cancel out the n's. So if you do that, you're going to get the sum from n equals 1 to infinity of 1 over n minus 1 factorial times x to the n. And then notice what we can do here is If we instead start at n equals 0, then what we can do is rewrite this as the sum from n equals 0 to infinity of 1 over n factorial. That's not what I meant to write. Oh boy. 1 over n factorial times x to the n plus 1. Right, so if we reduce this by 1, then all we have to do is increase these numbers for n by 1 as well. Then this is actually the same as this sum. So that's a bit fancy, you don't have to do all that, but the takeaway is that this is our answer. Right, our first four terms, our first four non-zero terms are these four terms right here. That'd be our answer.